last time we talked about spur gears. They face to each other, and the transmission of loads between the teeth from both sides follow a tilting line, which is having a pressure angle against this tangent, you can say tangent surface between the two gears. Okay, so that's pressure angle. So if we take a look at this gear set, now we have 3 gears connected to each other, and if we focus on the one at the middle, gear B, in this case, we need to focus on what's the orientation of the gears. How does each gear rotate? And then we can think about, we need to identify what is the exact direction of the load. So in this case, in the left figure, you can see an arrow right here. So this is indicating that there could be a motor or actuator connected to gear A. So it's driving gear A. So this is the driving gear. The other 2 gears are driven by gear A. Okay, so if I have a small gear right here, which is rotating counterclockwise, then we can think about the tooth right here. It's pushing the tooth on the other side. It's being pushed, and the angle, pressure angle, should be like this way. Should be drawn in this way. And that's why if we observe the free body diagram of gear B, the external force coming from gear A comes from this direction. Okay? Now, then we need to observe the relationship between B and C. Since gear A is rotating counterclockwise, then gear B is rotating clockwise. Okay, it's rotating clockwise. So if there's a tooth right here, it's going up. And on the other side of the gear C, it's holding the position and trying to push down. So if there is a reaction force, the tooth of gear C is pushing downward to form this low balance, force balance. So it's pushing downward. So in this case, if you observe the profile of the tooth, the force should be transmitting along this line, this direction. And you know, the force coming from C applying onto B should be going this way. That's why we can tell the external force right here is this way. Okay? Once we know the external force, we need to observe what's happening at the center. Basically, these forces are the force that are between the gear itself and the shift. So this is basically the reaction force coming from the shift. So the shift is holding right there and it's trying to push your gear. Okay, so this is reaction force. Reaction force from the shift. So if you are studying the shift, then, so if we study, let's say the shift looks like this, okay? And let's say this is the position of the gear, and let's say the orientation is like this, X and Y. So here is Z. Okay, if the orientation is like this, and since this force came from the shaft, so the gear will push the shaft on the opposite direction. So there will be a force going this way. Okay, and so that will be the force coming from the gear. So how come the gear is pushing the shaft? Because of the reactions between the gear and other gears. Okay, so when you are designing a shaft, axle system, there are multiple components. Every two components connect to each other has a force reaction between them. So you need to focus on maybe one component, and then you need to figure out what's the forces coming from each other. Okay? So this is how a gear design is actually related to a shaft design. Okay? So for the shaft itself, due to this force, there could be bending and shearing force, and this is a problem that we solved in the past. Okay, but now this time we tell you, okay, something on top of the shaft, and there's force inside that particular component. And today we are talking about gears, and this is a case of a spur gear. Okay, and we also need to be aware of other kinds of gears because of how the teeth profile look like. The force comes from different directions. Since the force comes from different directions, that really affects how you analyze the force balance. Okay, so let's pretend this problem is designed differently, and I use a different color. Let's pretend this is going this way, and this is the driving direction. Okay, so there's a motor driving in this way. In this case, this tooth is pushing this way, so it's going this way. And in this case, the pressure line is going this way. So the external force actually comes from here. So the problem changes completely. This is no longer the external force. The external force comes from this way. If we drive the gear different in the opposite direction. Since this gear A rotates clockwise, gear B will rotate counterclockwise. So the tooth right here is going to push the tooth right here. So it's going this way. Going this way. And since the tooth on B pushes the tooth on C, so the tooth on C pushes back. So it's pushing back here. So that means the external force right here should be in this way, not this one. Okay? And if we have different directions of reaction forces, external forces, then the reaction forces will change its direction. But in calculation, you don't need to swap the direction because the math, the solution process of the equality equations will give you negative values at the end. So at the end, this may be swapped to some other direction. So when you define the reaction forces, this is still okay if you define this way. And the math will tell you whether this is positive or negative. Okay? But those two are important. If you define those two in a wrong orientation, then it's completely wrong. Okay? So the conjugate relationship between the teeth from both sides, and whether it's rotating clockwise or counterclockwise really matters. Okay? It affects the direction of the external force. Okay, so those are for your reference. Now I want to move on to different kinds of gear. So this is bevel gear. Last time we already mentioned the bevel gear, the teeth lies on a cone shape, a cone, right? And because of that, the force between the teeth from each side is really coming from a particular angle. That force is not parallel to any axis. So for a bevel gear system, we have three directions. We call this one is the axial direction, okay? And if we focus on this position, so coming from the center toward outside, this direction we call the radial direction. Okay? And there is one more direction which is this direction. So what is that direction? That direction is like a tangent direction. If you view from the side, it's like this direction. Okay? It's like talking about the forces that is tangent to the circle right here. And we usually call this kind of direction transverse direction. In Chinese, it's like a 横向. Okay. Axial is like a 轴向. And axial is 径向. Yeah. If you need those translations, I wrote it down for you. Okay, so the forces between the teeth from one side to the other side is not parallel to each of those directions, which means that force has directional components in all three directions. So this figure is showing you this vector W is the force that is pushing from the other side of the tooth, and then this W vector has three directional components: the WA axial, WR radial, WT transverse. Okay? So now you know for the teeth that is not straight, it's like tilted along some direction. For those kind of teeth, it's more troublesome. The force analysis needs to consider force components along all three directions. Okay? So, this is a problem I usually give my students for exams or homeworks. We can take a look at this particular problem. I really like this problem. because this problem has a set of bevel gears and also 2 cylinders, and it even shows you the position of bearings. So it's really a kind of system that can be seen in practice. Okay. Does anyone know how those gears are being assembled to a shaft? Can anyone tell me some particular methods to put them together? Yeah. Yes, you're right. So usually there is a slot for the key. Okay, so for the shaft, you will have a slot for the key, and you have a slot on the gear itself, and there's a key inside. But if we have key at the middle right here, this gear could be sliding up and down, right? How do we avoid sliding? What do we do next? Do you know? What can we do? Just how to tighten it. No, use a screw. It's very easy. You use a screw. Just drill a hole and then have a screw to tighten it. Usually that's the way. Or maybe for this system there are some other parts. For example, if the shaft is having a wider portion, maybe not this tall. For example, if the shaft has a wider portion right here, you could have screw right here. Okay, either way, there are many ways. But the way I like this problem is it allows me to think about, okay, in the future, if I design this, how do I truly assemble this? Okay? So there are many ways, but that was just one of the ways. And in this problem, it also talks about some very practical situation. And let me go through the wordings and please pay attention to what happened. Okay? So it says there's a bevel pinion. So which one is bevel pinion? Bevel pinion. This one or this one?
Oh.
Which one?
Oh.
No. Small one is bevel pinion. Remember we have so-called a gear and pinion, right? And I mentioned the bigger one is the gear, and the smaller one is the pinion. Okay, so when a sentence say bevel pinion, it's telling you is this one. Okay, that's why we need to know, we need to understand what's going on in words. Okay, so bevel pinion rotates at 600 revolution per minute. So it's telling you this one rotates at 600 RPM, revolution per minute, right? This one. In the direction shown, and transmits 3.75 kilowatts to the gear. So it's driving, and there's energy being transferred, there's power transmitted to this gear. So the driving power is 3.75 kilowatts. Okay. The mounting distance, the location of all bearings, and the average pitch radii of the pinion and gear are shown in the figure. So basically all dimensions are shown in the figure. For simplicity, the teeth have been replaced by pitch cones. that means when they draw the bevel gear, they don't draw that 3D structure. They just draw the cone. And it's indicating it's the pitch cone. Because only the pitch circle tangent to each other. And for bevel gears, the pitch cone tangent to each other. Okay? So you can think of bevel gear sets are like two cones tangent to each other. Okay? And the teeth lies on the pitch cone. So it's like, okay, I have a tooth right here, another one here. Okay, it's very difficult to draw, but it's like this. Okay, if I draw another one. Anyway, okay. So for simplicity, only pitch cones were drawn. Bearings A, C should take the thrust loading. That's the very practical condition in this problem. And let me tell you what's going on. Bearing A, okay, this is bearing A, bearing C, bearing C, okay? How come the problem specifically tell you those two bearings are taking the thrust loads? Okay, let me explain more what happened. So if this is the driving motor, if this is a driving gear, that means I may have a motor right here. Okay, it's driving this particular gear, and those two gears are connected to each other, so the power is being transmitted to here. If two gears are connected to each other and it's pushing each other, and it's spinning so fast, every minute it's rotating 600 times. It's really fast rotation. So a lot of force and power is being transmitted from one side to the other side. If on each side there's nothing holding the mechanical component, it will fly away immediately. Imagine these two shaft systems connect like this, and if nothing is holding the shaft or the gear, when you put them together, when you turn on the motor, the driving force is so large, this gear will be pushed away. So something must be holding that strong power. So when we talk about thrust, it's like the power to drive, to rotate, to push. Okay? And it's telling you that power is being holded, that force is being holded by the bearings. So there is a very strong pushing force onto gear bearing C. So since all the driving force coming from this side will be held by bearing C, this one actually doesn't hold the axial force. And the problem specifically mentioned all the thrust loads applied to bearing C. So mathematically, when we solve this problem, when we try to analyze the reaction force, there could be reaction force. For example, this could be RD. Along, we can give there's a y coordinate system. We can claim this is x. There's x right here, right? So we can say this is reaction force at D along x direction. Okay. Do we need to do this? RDY. No. This equals to 0 because the problem tells you it doesn't carry the thrust loads. This one carries. So when we solve it, this is reaction force at C along X, and this is reaction force C at along Y. This is what the problem is talking about. This load exists, this reaction force exists, but this one doesn't, because only this one is carrying this actual load. Okay. Similarly, over here, this one carries all the loads. So this will be reaction force at A along X. Here is reaction force A along Y. But this one only reaction force B along Y. It doesn't carry the actual load. Okay, so this is what happened. Okay, how about the forces between the gears? It's right here. It's right here, and it's following some particular angle, pushing. If you are talking about the force from here to here, it's pushing like in this way. You need to have good imagination about how the tooth look like, and then you can kind of imagine how this vector is directing to, and then you can based on some derivations in the past, you can find its directional components. Okay, so let me show you if we draw the free body diagram. It's going to be like this. Okay, so I'm going to erase some part. I think a problem like this is so important for mechanical design. When you find a job and your job position is mechanical designer, basically in your company, you will be designing mechanical components. If you are really good in CAD drawings, of course, you can operate a software and draw the components. If you have some good sense of art or product design, you can make products that looks nicer. But if you doesn't have the sense of mechanics and the material in this course, what you design may fail. This is actually more important. Okay, so let me copy a picture right here and place this next to, make them side by side so you could understand what happened more easily. Actually, this was better. So in this particular free body diagram, you first want to realize the coordinate system. This is y, this is x. So that was x, this is y, okay? So we are taking a look at D and C. So here is D and C. So those two are the locations for the bearings. And as I mentioned, only the reaction forces that is perpendicular to the arc of the cylinder, to the cylinder, will be seen in D. So these two are the reaction forces perpendicular to the cylinder. We don't have the one that is parallel to the cylinder because this one doesn't carry the thrust. This one does. Okay? So the problem tells you when the force is pushing from this side to to the bigger side, bearing C carries the load. So the problem is talking about this reaction force. If we don't truly understand the problem and we didn't define the reaction forces properly, this problem cannot be solved in the same way. Okay, of course, in reality, maybe some portion of the, maybe this gear bearing carries some portion of the thrust load. That's of course possible. Then in reality, you may need some sensors to realize how much load this is carrying. But in this particular problem, the problem tells you this carries the entire load. Then you need to realize, okay, this one has this axial reaction force. Okay, now let's take a look at this particular point. That is this guy. Okay? And we need to figure out how come the three force components look like that. Otherwise, we may analyze the problem differently. So from here, there's an arrow like this. Okay, so it's telling you it's rotating in this way. So it's like it rotates in this way. Okay? From here to here. So if this pinion rotates in this way, that means the gear right here rotates in this way. Okay, it rotates like this. Okay, so if this is the case, then this gear is definitely pushing the gear right here. So it's like a pushing from the back toward you guys. Right? Can you see it? It's pushing toward you. So definitely the transverse force is coming from the board toward you guys. So the transverse force goes this way. So what is this direction? X, Y, and Z. So the transverse force goes up along the Z direction. That was Z. This is how you observe where the load is pointing at. Okay? And since this guy is always pushing this guy, so there's always some kind of force pushing this way toward the center axis of the bigger shaft. So no doubt we can have a radial external force pushing toward the center of this cylinder. So this guy definitely is there. It's easy to realize. But the other one, the WA, is harder to visualize. So from here, you can tell it's actually like this, WA. And this is WR, okay? I think it's not that hard, actually. From here, you realize, because the profile of the pitch cone looks in this way, there is a tilting boundary. And of course, as we mentioned, this cone is pushing the other cone. So definitely there's a force not only coming from the radial direction, and also another force coming from the axial direction. So actually it's not that hard, okay? So you just need to realize how a gear is pushing the other one. Then you should be able to define those force vectors along the right direction, okay? So, in this particular problem, for the very important step at the beginning is to define the vectors in the right way. Okay? And also, there will be reacting torque. How come there's reacting torque? Let's think about the bevel gears. When we have bevel gears, and if the external force comes this way, and the reaction force comes this way, then we are sure the force couple will rotate clockwise, and there should be a torque rotating counterclockwise to balance the force couple, the moment generated by the couple. Okay, so in this case, it's also happening in this shaft system. So the only thing that we need to understand is which direction this torque is. So in this case, if we view from the right, and if we draw like this, we know the transverse force goes this way, and we're viewing from this side. So we can visualize the WT and WR, but WA has nothing to do with the observation along this direction. So it's going this way. So the combination of these two actually forms a pushing force along the pressure angle. So definitely at the center of the shaft, there is some kind of reaction like this. And these two forms a force couple. It's generating a moment that is going counterclockwise. Therefore, at the center of the shaft, there must be a reacting torque to balance the moment that is generated. That's why this torque goes clockwise. Okay? That is very important for the free body diagram. Okay? Usually, defining this defines how you get around 80% of the score. Because usually the mistake comes from a diagram like this. And the rest are just calculations. You just plug in numbers and then solve for it. But here is the key. Okay? So this is about bevel gear sets. We can learn more about other kinds of gears. Very similar to bevel gear sets. This is a helical gear. And since the T profile is not straight, it's also having an angle. So for helical gear, the force is also having three components. Again, we use the same terminology. T for transverse. Okay, so like following the tangent direction of the pitch circle. And R is radial. Radial is always the direction coming toward the center. And A is axial. So axial is always the direction that is parallel to the center axis. Okay, similarly, for helical gears, we have forces along three directions. And for all kinds of analysis, it's the same. Once you build up the free body diagram, if there is a helical gear and you already identify the three components of the external force coming from the other side of the gear, then all the rest of the calculations is the same. Okay? Just like a problem like this. Okay? So for this one, I'm not going to go through to spend too much time. For this kind of problem, there's force right here, and it's going toward some kind of direction, okay? And right here, it's telling you, okay, there are 3 force components. Okay, that was the point right at the tangent point between 2 pitch circles. And over here, you can realize for gear force transmission, there's always torque at the center axis. Same reason, okay? And for the bearings, in this problem, this one is carrying the thrust. Same reasons, okay? If you understand the previous problem, this one actually is the same problem. Only difference is how the gear looks like. The shape looks different, and of course, when you derive some equations, there could be some slight difference. Okay. This is about worm gear. The worm gear, actually, worm gear, the profile of the worm gear is very similar to the bevel gear or helical gear. So I don't want to spend too much time. I think it's enough for us to understand what happened. And just a quick, just a diagram of how worm gear sets look like. Okay, this is the one that looks like a worm, and this is the gear. Okay, and the force between them also follows an angular direction. Okay, now I want to move on to a very important force analysis in gear. Like I said earlier, for spur gears, we not only need to analyze the shaft, we also want to analyze the gear. In the previous problem, we can understand the forces on the shaft, but how about the gear itself? The gear has multiple teeth. Each tooth carries loads, but the load inside is very complex. So usually, it's almost impossible for you to formulate an analytical equation. It's almost impossible for you to analyze it by some kind of analytical solution. Because different size of gears has different shapes of the teeth, and the structure looks different. It's not like a rectangle, you can model it. So what happened is, there's a guy called Lewis, okay? So he formulated this kind of model to simplify the force analysis inside one tooth of spur gear. So he derived general equations for the force analysis in each tooth. After his development, after we have the equations like this, we can estimate whether this tooth can carry the load. So what he did was, he considered this shape as a rectangle. Okay, he simplified this as a rectangular like a rectangular cantilever beam. Okay, so when you see a figure like this and you see something being drawn like that, this is the cross section. It's just trying to tell you this is the width of the face. Remember when we talk about the terminologies of a gear, we say this is the pitch circle, and we said this is the face, this is the flank, and here is the width of the face. Okay? So this is just telling you how thick the gear looks like. Okay, so you can say it's like if you try to draw this in 3D drawing, if you draw it this way, it's like you are viewing from here, and this width right here is F. So for a drawing like this, it's just placing the cross section, rotate by 90 degrees, and put it right here, just to tell you how the cross section looks like. Okay? So this is a simplified model of the complex tooth, and you can tell from here that there's a T right here. It's telling you how wide this tooth is, and that's why in this model he used the same width. So this is how come he used this T? How come he doesn't use this one? Can someone guess why he used this? Maybe this one makes more sense. Can someone think about it? I can think of 2 reasons. Anyone want to try? Just
It's weaker.
maybe sometimes it's smaller, because for some kind of gear shape, sometimes it looks like this. Sometimes this could be narrow. Sometimes, if you design some gears, sometimes you have a shape very strange, because this is based on the involved line, and sometimes it's narrow. My belief is it's easier to measure. If you have your measurement tool, it's easier to measure. Okay, if you measure in this side, you just don't know where to measure, right? If you didn't measure properly, you may measure wrong the length. But here, when you use the Yoga it's easier, right? And also, this width is more important, more related to the strength of the teeth, of the tooth. If I have a geometry like this, when I apply force, all the stress concentrate at the neck, right? Okay, so if I have exactly same geometry but slightly thinner or slightly larger, maybe it doesn't make a difference. The thickness right here doesn't make a difference. The thickness right here matters, because this is how much material you have at the position that really carries the stress. Okay, so I believe that's the 2 reasons why we use this as the key parameter, okay? And also, previously, why do we need to know how to measure the transverse force? This one. This is the transverse force. Because when we try to analyze how strong the tooth is, we need to know how much load is generating the bending. Only this one is trying to bend this cantilever beam. This one doesn't bend. And you never see a tooth being crushed by this force. You only see a tooth being bended and break. So the transverse force is more important for force analysis of the tooth. That's why in this model, they don't even care about the force along the other direction. That doesn't break the material. Okay, so in the simplified model, only the transverse force is being analyzed. So there are a bunch of equations that they are using the equation based on the analytical solution. So this one basically is the MC over I, right? We already know this. They're using MC over I. But they just plug in all the parameters to get this number, to get that equation. So what happened is how they define Lewis parameter. So what is a Lewis parameter? Inside gear parameters, there are two important, actually there are several important dimensional parameters. So one of it is this one, x. So how do they get the x? They based on geometrical shape. He is drawing a line here and then perpendicular, a 90 degree, and then getting this x. Okay. So they're using the symmetry of geometrical symmetry to get this to get this shape, and they realize if I have different length of x, that will indicate how this triangle looks like. And when this triangle is having a wider range, then you may have a fatter tooth. When this triangle is narrower right here, you have thinner tooth. So this x could be used as a representing dimension. But what Lewis is trying to do is to form dimensionless equations. Dimensionless. No dimension, okay? So one way to create dimensionless equations is to have a dimensionless parameter, which is y right here. So what he did was he put x right here, and he put circular pitch right here. So pitch is also a very important parameter. It's telling you the arc length between two teeth. So basically how frequent you see the teeth, right? So with those two key parameters, you can form a dimensionless factor, and it's called the Lewis form factor. It's like a shape parameter. And how come he likes to use, how come he used 2x over 3p? The main reason is because when he derived the stress, there are terms of 2 and 3 inside the equation, like over here. There's 2 over 3 right here. He wants to get rid of the coefficients. So if he defines y in this way, 2x over 3p, he can later on get a very simple one like this. This is a very simplified stress equation. So let's take a look at what's inside the stress equation. This is basically the transverse load. Okay? So what's the usual way to define stress? Force over area. So let's take a look at what's this. This is the width of the face. Okay? So what's this? P times what? P is pitch. So it's like y times p, and you will get a number. So it's like you will be getting some length right here, which is py at the end, and you will have f. So fpy would be what you get at the end. It's an area. It's a stress area that was being calculated, estimated based on Lewis factor. Okay, so at the end, it's not directly like telling you what is the transverse force, okay, and then tell me what is the area. It's not like that. It's not like you just use F times T. Because Fpy ends up with some number that is not F times T. But he derived from sigma equals to mc over I, and he has a shape parameter which is dimensionless. At the end, it equals to a very simplified model, and this area right here equals to Fpy. Y right here has no dimension, it's a shape factor. P is the circular pitch right there. So F and P would be some parameter that could be determined very easily. When you design the shape of a gear, you definitely know the thickness of the gear, and also you have to define what's the pitch. So with this equation, you don't even need to measure the size of the gear. So what the beauty of this Lewis form factor is that when we derive, I said maybe we need to measure T, or maybe we need to have a triangle right here and estimate X. But in fact, at the end, if you define in this way, you don't see T right here, you don't see X right here. You only see F and P. F and P are the parameters that you get easily from your gear design. So that's the beauty of this, okay? And that's how you can easily estimate the stress. But is it accurate? It's not accurate. So this is the basic equation, and since it's not accurate, how come a simplified equation can be used for all kinds of gear shapes or all kinds of gear operation conditions? there's no way. So at the end, what they did was that perform a lot of experiments. And if in some particular situations we have to correct the equation, we correct it. So in the following slides, the book is trying to tell you there are all bunch of conditions that we need to think about, and there will be multiple factors to correct the equations. And I will show you what the final equation looks like. There are so many of them. The book actually categorized in this way. The textbook tells you at the end, the stress equation should look like this. And you can tell, okay, I still have my transverse force, okay, I have my phase width, and the book kind of reorganized the equation a little bit. They don't use small p anymore, they use PD. PD is the diametral pitch. Diametral pitch is PD. And PD is the reverse of the module. Okay? If you, I can show you the previous slide. At the very beginning, when we talk about, okay, this is PD. Basically is number of teeth over the diameter of the pitch circle. D is diameter of the pitch circle. Or you can call pitch diameter. Okay? And capital P is the inverse of module. Okay? So it's a parameter that we know when we design the P. So this portion at the end, they don't use small p anymore, they use PD. So PD represents some parameter that is has a relationship with small p. And you can then see a lot of K's that was not mentioned earlier. Actually, they were covered in the slides that I jumped through. So let's take a look at what are those K's. So there's a KO, overload factor. So if the working condition of the gear has different loading scenarios, different loading conditions, this K needs to be changed. Okay? KV. KV is so-called a dynamic factor. The reason why they use V is because this factor depends on the velocity of the K. So when you rotate the gear faster, there are more concerns about the strength of the gear, of the T. KS, size vector. So if I have everything the same but different sizes of the gear, there is a factor as well. Km. Km is a load distribution factor. So in some cases, if you have a larger teeth, the face of the teeth is larger, you may see uneven distribution of the load. So this factor tells you, okay, if that happens, you need to multiply some number. KB is the rim thickness. Okay, I never tell you what is a rim. I never tell you what is a rim. So I'm going to tell you now what is a rim. It's not included right here. Or maybe, okay, in the back. this is like the rim, R-I-M, rim. This shape is called rim, and the thickness of the rim, okay? So if you have a gear that has a huge hole at the center, then the thickness matters, okay? So the rim could be bending because it's not completely structured with material. It's empty inside. So the ring could be bending. That's why they have correction as well. So let's get back to the general equation. Okay, so over here, like I said, the stress not only depends on the equation came from Lewis factor, but also has a lot of correction factors. And there is a J factor. J is related to Y. Y is Lewis factor. Okay? So J is related to Lewis factor. Okay? So, in the future, when you design a gear, you need to know it's not that easy. Okay? You need to be aware of the operation condition. Otherwise, gear may fail. Okay? But this is only the stress. How about, do you remember our design equation should be like this? Stress smaller than your strength. The force must be smaller than how strong you are. So this calculation is only talking about the left-hand side of the equation. How about the right-hand side? Do I just use Young's modulus? What happened is, no, it's not that easy. This is the right-hand side of the equation. So let's take a look at the right-hand side of the equation. And let's see what will affect the strength of the gear. So on the right-hand side, we have ST. What is ST? Allowable bending stress. Okay, so this is like a allowable stress without consideration of anything else. So it's like a allowable bending stress for the material. You can use the Young's modulus to estimate, okay, what would be the allowable. Definitely, allowable bending stress is very related to your material property. Stronger material allows stronger bending. Okay? So ST is allowable bending stress. Yn is so-called stress cycle factor. So as you have more cycles, the bending stress, the bending strength drops. Just like when we talk about the fatigue problems. So gear also has cycle issues. If you have cyclic motions, the strength will drop. Okay? Then KT this guy, T is temperature. Okay, then over here is telling you when the gear is under different temperature, the strength changes. Okay? And also reliability. So it really depends on how reliable you wish the gear to be. Do you wish the reliability to be 99.99% or just 98%? Okay? Different percent of reliability changes this factor. If this factor changes, your design equation changes, then that affects a lot of your decision. Finally, the last one, SF, is the safety factor. Okay? Safety factor. So right here you can realize, okay, it's a lot of information, and what will be the final design equation? It looks like this. So when you design a gear, actually what you need to do is if you worry about the strength of the tooth or teeth, what you need to do at the end is actually this. The stress must be smaller than the allowable stress, and so many parameters. Let's count how many. 1, 2, 3, 4, 5. J, you can say is a parameter as well. 6, 7, 8, 9. It's more than 10. More than 10 parameters. So in gear design, if you want to monitor the health of your gear, you need to be aware of more than 10 operation conditions. That's how complex a gear design is. Okay? So please remember, it's not easy. That's why I recommend you to buy the textbook. If you have a textbook, when you need to use it, the book has all the equations. Okay? If you try to get reference from Wikipedia or try to find a research paper, sometimes information is not put together. A textbook is the most useful tool for you to do this. Okay? Let me go back. Okay, for gear design, there's one more thing you need to be aware, but I'm not going to spend too much time. It's something called the contact stress. Contact stress is based on this theory, okay? So when two objects conjugate with each other and a very huge force is being applied to two objects, they are being pressed, and there's a particular area, it's under high stress. This drawing is indicating how much stress concentrated at this area. So this kind of contact stress is actually not considered in previous analysis. For bending, we don't care about this local concentration of stress. But actually, this is important for conjugating mechanical components. So there is some model to estimate the profile of the concentrated stress. And there are theories of contact stress. I can tell you, this is definitely not the only theory. I believe there will be a lot of models in research papers. I just want you to understand for conjugating objects, conjugating mechanical components, there is something called contact stress. Contact stress will cause damage of the surface of the teeth. So there are two kinds of damage to the teeth that will lead to failure. One kind is when the teeth bends too much and break. That is based on bending stress. The other kind is the contact stress is too hard and the profile is being damaged. You have wear. Do you know wear? Wear. Wear is like wearing clothes, but in English, the wear has a different meaning. 磨耗. Okay? So contact stress will cause wear on the profile. So if you do not have a very smooth profile of the gear, you can cause vibration. That's trouble. That's trouble. Okay? So for the stress analysis inside the teeth, two kinds of stress need to analyze. One is the bending stress, the other one is the contact stress. And let me show you the final equation. This is for bending stress. This is for contact stress. Then you will realize how come there is a square root right there. How come it looks different? Because of the model of this one. Okay, in this model there is a square root. Okay, it's trying to calculate the width of the concentrated stress, and it's calculating the half width. And the calculation has square root. And therefore, when you derive it, there's always square root. Like here are talking about the contact stress. There's always square root. So at the end, for contact stress, it's a bunch of equations as well, and you don't need to memorize it. Just be aware. For gear design, contact stress is something also important. And there are some parameters that is the same as the bending stress equation, which is good. Okay? And the allowable contact stress is right here. For contact stress, there is also a allowable limit. So please make sure you understand this. That's it. That's everything for what I want to tell you about gears. So that finishes this week's introduction. For more, if you want to learn about gear design, if it's about kinematics or dynamics, you need to take other courses. In this course, we only focus on the force analysis and the strength. So the textbook for mechanical design usually spend a lot of time on what I told you today. So in the first part of gear analysis, I introduce you that the external force onto the teeth could be lying on different directions. So you need to be aware, okay, there's a transverse force, radial force, and axial force. If you can do correct force analysis, then you can move on to stress analysis. So two very important knowledge about this week's lecture. How to do force analysis, free body diagram. And then second, what's the stress? And usually when we have exams, we don't even ask students to memorize the equation. Too long, too many equations. We just give them the equation and a lot of tables. I can show you the tables. It's all about checking the tables, check the numbers. Let me, okay. So take one example. This is one of the factors, J. This factor depends on helical angle, so different shapes. And these are different numbers of T. And when you see a table like this, you can be 100% sure that these curves were obtained by experiments. So there must be some researcher already done a lot of research. He got a lot of experimental data along the curve, and he draw a curve to pass through. So if you have a table like this and you are sure it's not analytical, it's based on experiments, this curve basically is a statistical approximation. Okay, so basically all the parameters that we have here are based on approximations. They are never accurate. So it's very difficult to truly derive the right equation just to determine J. If you do not, basically there's no way. So only way is to do a lot of experiments and then draw a curve. So in the future, someone needs it. Okay, my Healy's angle is this. My number of T is this. Okay, my J must be this. But he only did these. He only did 20, 30. How about 80? So okay, approximately 80 is right here. Okay, my J is here. Maybe 80 is here, 80 is here, but very close. You can only just check table and then get a rough number. Okay, so in mechanical design, you always face issues like this. A lot of numbers are approximations. That's why safety factors are so important. But how safe is safe? Should I increase the safety factor to 3 or 2 or 5 or 10? You just don't know. Okay, so last week I went to an international conference. There was a keynote speaker. He was doing mechanical designs in semiconductor. He also faced the same issue. You know, in semiconductor, the components are so small, they are in micro scale. How do you analyze the force inside? He just couldn't do it. There's no such kind of sensor that is in the scale of nanoscale. Because the smallest sensor that we can make is already probably in micro scale. How do you use a sensor that is in the same scale to measure the geometry in micro scale? You can't. Okay, so what he did was he used ANSYS. He used ANSYS. And in the keynote speech, he already tells us, in every particular situation, you just don't know what parameter you should use for your ANSYS model. If you tune the parameter a little bit, like enlarge some numbers, the result changes. So which one is right? You just don't know how the model could be right. So which one is right? The one that is closest to the reality. So what people usually do was they have experiments. And in the experiments, they can measure something. And in the theoretical part or numerical part, they they just try their best to get as close as possible. Once they have something, okay, it sounds like it looks like a pretty good model because this model matches the reality. Then people start to use it. This is similar situation. In this book, almost every diagram and table were provided by manufacturers. So if you check the book, it tells you this data came from some company. So that company, they try to sell their gears. They manufacture gears. So they work with the author, they provide them tables, and the manufacturer did a lot of experiments and defined those equations. The advantage of showing those tables in the book is that students will use it. So in the future, when they go to a company to work, they will tell the company, hey, I'm using this book, and this book is using this brand of gears. And this brand of gears has equations. Let's use this brand of gears and use their equations. So that's why gear manufacturers or all kinds of component manufacturers are willing to put data in here. This is the best promotion. They started to promote when you guys studied the course. Okay? Anyway, so that's everything I want to talk about for today.